Hello everyone, this is Shiva. So in the last video we've seen electric field for a point charge. Now we'll see for continuous bodies. So as I said, I'll make a series on continuous bodies, not just electric field. I've also created another playlist where I'll be incorporating the other continuous bodies problems, that is moment of inertia, right, center of mass, gravitational field and potential, etc. So yeah, now we'll see for electric field. So this is for a thin wire or rod, right, which is a finite length. So so this is a finite length wire or rod. Here I considered a small element of length dx, right, and from this rod I considered a point P which is at a distance d, right, and I connected this and rod and I've drawn a normal here, right, and this is distance d, and from this point where I've drawn normal, from this point the distance between this point and the considered small element, the distance between that is x, right, and this is d. And then since this makes a right angle triangle, this distance, right, the actual distance between the considered element and the point, that will be root of x square plus d square. So since this is a point charge, I can directly write k is equals to kq by r square, right. So that's what I've written here. So E is equals to small electric field due to small element dx here, so that would be in this direction, since electric field is a vector quantity. This is dE, and that dE magnitude is given by kq by r square. K small charge for this one, dq, divided by distance of the square. Actual distance is root of x square plus d square. If I square that one, this is the x square plus d square. So this is kq by r square. Here charge dq is the small charge, so dq I can write as lambda dl, right, and dl is the length of the element which we considered, and here the length of the element which we considered is dx, so that's why I've written here lambda dx, and this is the one I've substituted here, lambda dx here, right. So this is the small electric field due to this small element at this point, right, and this in this direction. And if I consider this angle to be theta, the same angle here it would be here, right, theta, and if I resolve it into components, this would be dE cos theta, and the other perpendicular component, so this is dE sin theta. So away from the rod, so that's since arbitrarily this I've took as x direction, so that's why I denoted with ex, and since this is in downwards y direction, I've just took it as ey, right. So to get ex component, total ex due to this total wire at this point, I should integrate this component or this element dE cos theta. So integrate dE cos theta, right, d which we have written already here due to the small element, and cos theta term from this triangle, right, from this triangle. So cos theta is adjacent by hypotenuse, that is d by root of x square plus d square. Here I've written here, right, so multiplied this thing, and yeah, from the triangle I've taken tan theta, right. So tan theta, if I take opposite by adjacent, so tan theta is equals to x upon d. So from here we got x is equals to d tan theta. So dx is equals to d secant square theta d theta, and if I substitute that here, I've got this, right, and here I've used a trigonometric identity, secant square theta minus tan square theta is equals to 1. So from here 1 plus tan square theta I can write as secant square theta, and secant square theta, if I write it as whole square, square get cancelled, so that will be whole cube here. So k lambda by d and integral, so everything cancels out here, d, 1d will be remaining here, so that's what I have written here. So 1 by secant theta goes to numerator, cos theta, integral cos sine, and now the limits. Now I should this element, if I traverse this element, right, if I make it up and if I make it go up and down, it should cover the total length. So if it goes uppermost point of the wire and the lowermost point of the wire, so uppermost point, if it goes, it would subtend an angle alpha 1 at the considered point, At the same considered point, if this goes down here, it would subtend an angle alpha 2 here, right, at this point, from this normal, right, from head by this one. So this is alpha 1, this is alpha 2. So taking this as reference, since I'm going down here, right, downwards, I took it as minus alpha. Since I'm traversing upwards, so I took it as plus, right. So that would be minus alpha to 2 plus alpha 1. So k lambda by d, if I substitute this, upper minus lower, and sine of minus theta is minus sine theta, which gives us minus minus plus. So k lambda by d sine alpha 1 plus sine alpha 2. This is Ex, right. So this component which is away from the wire or rod, right. So and also you can say this is kind of perpendicular, so this is a perpendicular direction. So yeah, I just as I said, since this is in x direction, I took it as Ex. You can take Ey also, doesn't matter, it's just notation, right. So as for this component, I followed the same procedure. Just instead of cos theta, I've substituted sine theta here. So from this triangle, sine would be x by root of x square plus t square. So if I substitute that here, so we got this same thing again. From the triangle, I've written x is equals to d tan theta. Again, dx is equals to d secant square theta d theta, right. And if everything cancels out just like before, and the remaining things would be this one, k lambda by d sine theta, and integral sine theta would be minus cos, and again the same limits, minus alpha to 2 plus alpha 1, right. And if I do this, we'll get this relation. And here minus theta, right, cos of minus theta would be cos theta, even function, and this would be our Ey, right. So Ex and Ey we got. So Ex component is just this one, right, sine terms we got, and Ey component, right, this is one. So this is for finite wire, where lambda is line charge density. If this wire goes to infinite length, right, in one side or semi-infinite or only one side, it could be anything. Let's just say it goes infinite length on both sides. So this goes to infinite and this goes to infinite. So yeah, while deriving that, this element should traverse all the, if I make this element go up and down, right, it should cover the total length of the wire, but here the length is infinite. So this element which we consider, it keeps on going on the either direction. So if it goes uppermost point, so the line joining the element and the considered point, this would keep on going, right, and this line would keep on going like this. So this alpha 1 keeps on increasing as we increase the length, right. So let's just say our point is here. So now my angle would be this much, right, and again here, again this goes. So I think you got the idea. So this goes like this. So this angle approaches to 90. The same goes with other side also. This angle approaches to 90 here. So alpha 1, alpha 2, both angles approaches 90. And if you substitute these angles, right, here for infinite case, so sine 90 plus sine 90, 1 plus 1, which gives us 2k lambda by t for infinite value, right. So Gauss I've written here is the same thing. We can derive it from easily from Gauss law also, right. Integral E dot ds is equals to q enclosed by epsilon naught. That I'll discuss when we discuss Gauss law, right. So anyway, so same thing for infinite wire. For Ey component would be 0 because cos terms, cos 90 and 90 would be 0, right. So this is for infinite wire. This could be semi-infinite also. Semi-infinite, one angle approaches to 90, other angle would be there, right. So one angle approaches to 90 because as the length approaches, the angle approaches 90. Another point that alpha you could substitute. In other cases, for the same finite length only, the point could be on the either end, at one end, right. It could be uppermost end or it could be lowermost end. If it is at lowermost end, this angle, which this angle, since the element can't go down here, the element max it can go up to here only. So this alpha 2 becomes 0. So alpha 2 becomes 0, and alpha 1 could be some angle, right? And by if this point is here, this point is here, this is alpha 2, then alpha 1 approaches to 0, then you can substitute just alpha 2, right? And again, if infinite wire is there, and if we consider the point at one end, so one angle becomes 0 and other angle approaches to 90. So this is for infinite wire only, but the considered point is at one end, right? So whatever end we substitute, the downward angle becomes 0 and the upward angle we have to consider. The upward angle, it becomes 90 when the length becomes infinite, right? Okay, so I hope you got the idea, right? So in some cases, instead of this alpha, they could give this angle, right? They would give this angle. So alpha 1, so this would be 90 and this would be 90 minus alpha, right? So in all the formulas, you could just instead of alpha 2, you could just apply 90 minus alpha 2 here, or 90 minus alpha 1 here. So sine becomes cos and cos becomes sine, right? I hope you do that by yourself. I think it's clear for you. Yeah. So I'll see you in the next video where I consider another continuous body, right? Thank you very much.